Okay, let's start with the determination of the soil water or soil moisture, as it's called sometimes, content by drying. This is a quite simple method. You just compare two weights with each other. Yeah? You calculate the soil moisture content for each of the replicate samples using the following equation. So what we want to calculate is the percent of moisture content. This is the water content, yeah, MC moisture content. And this is easy. You just calculate the weight of the moist soil minus the weight of the dry soil divided by the weight of the dry soil. Okay, and this gives you the percent of moisture content. Yeah, I think if you think this through, this is very easy. You just put some soil in a vessel, weigh it, then you dry it in an oven, and then you weigh the dry soil, yeah, and then you can, by just calculating the difference, you can calculate the water content. I give you an easy example here. So let's say you determined a weight of 102 grams for the moist soil sample. Then you put it to the oven, weigh it, and dry it, and then you determine 90 grams. So the weight obviously decreased because the water is gone. Okay, and then you calculate the moisture content in percent. 102 minus 90 by 90, divided by 90, and then you calculate 0.133, and this means you get a moisture content of 13.3%. All right, so this is a good result then, and you can use that for discussions. Second thing is the extraction of soil solution by centrifugation, and maybe filtration if you didn't do it, or maybe filtration in any case for the soil solution because you didn't obtain that in the field, but maybe if you didn't do the filtration for the water samples as well, you can do them as well in the way that I'm going to explain to you now. So centrifugation, this is a centrifuge. Yeah? So I guess everybody already saw a centrifuge. This is basically a rapidly rotating rotor, yeah? That lets these vessels here rotate very, very quickly. So if you got a suspension of solid and liquid material, it will be looking like that, so quite dispersed before you centrifuge, and then after centrifugation it may look like that. So all the pellets, all the sediments, solid materials is on the bottom of this vessel, and the supernatant solution is on top of it. And you can take and win and analyze the supernatant. Yeah, looks like this. Before centrifugation, it's all mixed. After centrifugation, you got the solid here on the bottom, and you got the supernatant solution on top. And you will then take this supernatant solution here and continue analysis of the solution. Okay, so here it says it's a device that separates particles from a solution through use of a rotor. In biology, in this example, particles are usually cells. In our case, these are soil particles, yeah? And yeah, okay, so after centrifugation, you take out the centrifugation tubes, as they're also called, and then you can do the following. You can take up the supernatant solution in a syringe, yeah? And then press the solution through a 0.45 micrometer filter. Yeah? So in this example, you got this syringe full of the centrifuge soil solution, or maybe the unfiltered water sample if you didn't filter it before. If you got this equipment, I'm not sure if you got this equipment in your laboratories. If not, you can also use a filter paper. Yeah? This pore width of 0.45 micrometers is used normally because this is more or less the size boundary between really dissolved materials and particulate materials. So all the particles with a diameter larger than this, they are not in solution, they're not dissolved particles. And everything that passes an 0.45 micrometer filter is considered as really dissolved. And we're interested in the dissolved materials. So everything which is larger than that will remain in the filter here and is of no interest to us. Yeah? So we use the clear soil solution after filtration, which may also be a clear water sample, depends on what you pushed through the syringe here, right? And we use that for further analysis. So this is the extraction of soil solution by centrifugation and filtration. So what to do with these centrifuged soil samples and water samples and filtrated materials? We want to do titration. Titration, here we see a typical setup of a titration rig. Yeah, that's a ring stand here. And then you have a burette here containing the titrator. So some standardized solution you use to drop into your sample. So here is a bottle with your sample, typically an Erlenmeyer flask, but can be any other glass vessel as well, containing the sample to be titrated with an indicator, maybe a color indicator. I'm very sure that you already know what I'm talking about here from your chemistry lectures earlier, right? Okay, so you got this burette here containing the standardized solution, for example, 0.1 molar hydrochloric acid or 0.1 molar sodium hydroxide solution, and you can let it drop, let it slip drop by drop into your sample. So what I want you to do is acid-base titrations. Yeah? That means we want to determine the acid consumption up to a sample pH of 4.3, and we use this amount of consumed acid to determine the concentration of bicarbonate, HCO3 minus, bicarbonate anion, normally the most important anion in soil solution and groundwater, and in most cases at least. Yeah? The chemical equation behind the mechanism I'm talking about is the bicarbonate present in solution will react with an H plus with a proton, which is available by the titration because we put an HCl into the sample. And this will form carbonic acid, H2CO3, yeah? And this will then continue reaction to CO2, gaseous CO2, which will then degas and go to the atmosphere and H2O. And by the consumption of H+, so by the acid consumption, we can directly calculate the concentration of bicarbonate. Okay? I hope this is understandable. Yeah? So every mole of H we consume here is determining 1 mole of HCO3 following this reaction equation. I hope you'll be able to calculate the concentration of bicarbonate from this information. And as an analog to that, we will also use the base consumption to pH 8.2 for determination of free CO2. Yeah? This is the other way around. So if we have free CO2 in our samples, we can add sodium hydroxide here, and the CO2 will react with the hydroxide here to bicarbonate again, and well, sodium will be released to solution then. So this also means that 1 mole of CO2 will need 1 mole of NaOH to build up this HCO3, the bicarbonate, and in turn we can calculate what the concentration of free CO2 in our sample was by just evaluating how much NaOH we require until we reach a pH of 8.2. This is obviously a base, yeah? So we will increase pH by this titration. We will, of course, decrease pH by this titration, and these are the pH values we aim for. I'm going to explain you in a second why that is the case. We use indicators, as I said. So either we use color indicators, yeah? And you will titrate until there is a color change, for example, from green to red, depending on what you're using, depending on which titration you determine. Yeah, so you will be advised by the technical staff about that. Or if you do not use color indicators, you can as well use a pH meter. So for pH determination, you will titrate until you reach a pH of 4.3 or of 8.2. Yeah, so you don't not necessarily need a color indicator. You can also use a pH meter.